Okay, so we are now going to proceed with the circuit analysis in the S domain. So I mentioned just now that there are two methods that can be used in solving the circuit problem, which is to be based on loop analysis, okay, and also node analysis. So I believe that you have learned this in a circuit theory in semester 1 or semester 2. Okay, so we know that for loop analysis, we need to use a Kirchhoff voltage law to solve for the problem. Whereas for node analysis, we're going to use a Kirchhoff current law to solve the problem. So that is why in the previous part 1 of lecture 15, okay, I did mention about the use of two types of transformation. Okay, let us proceed. Let us have the examples of capacitor first. So we have this equation, yeah, which is obtained from the basic equation of capacitor, IC of C dV over dt. And when we do a Laplace transform for this, we're going to have we are going to have two options. The first option is the voltage, so the current in terms of the voltage. So the circuit transform is looking like this. It's look like this. Whereas for the second type is the voltage in terms of the current, and this is the equation, and this is the circuit transformation. So we know that for this circuit transformation, it can be used in solving the circuit problem using the Kirchhoff current law, whereas for this circuit transformation can be used if we opt for Kirchhoff voltage law, yeah, in solving the circuit analysis problem. Okay, so I hope you understand why we have these two options, yeah. Okay, so let's have a look on method 1 if you have the loop analysis technique to be used. Okay, so step number 1, okay, you have to replace all the passive devices that you have in the circuit, which include the resistor, the inductor, the capacitor, and also the voltage source. So all of these components needs to be transformed into the S domain. Okay, for instance, the resistor need to be transformed into the impedance of R, which has been learned in part 1 of this lecture. For the inductor, need to have the impedance of SL and in series with the voltage source. And for the capacitor is the impedance of 1 over SC in series with the voltage source also. Okay, and the voltage source need to transform into the S domain. Okay, so this is what we have learned in part 1 of the lecture. Okay, number 2, once you have transformed all of these two components, you have to sketch the transform diagram. Okay, and step number 3, then only you apply the Kirchhoff voltage law to solve for the problem. Okay, let's have a look on these examples on the loop analysis. So we are having these examples here where we have a voltage source of 3 UT. We have a switch, we have the inductor of 2 Henry, and we have a resistor of 4 ohm. Okay, so the question is, we need to find the IT, this current of IT, when the S is closed for t bigger than 0. Assume the current source I0 negative is 5 ampere. So we have learned in part 1 that I0 negative is the initial current, yeah, initial current of the, in this case is the inductor, yeah, in inductor. So 0 negative means that this is the initial current of the inductor. Yeah, is given to be 5 ampere. Okay, so we are given that the switch S is closed for t bigger than 0, which means that initially the switch is open. So when t bigger than 0, then only the switch is closed, or the circuit is said to be complete. Yeah. Okay, so what you have to do that we have to adopt for the steps that I mentioned in the previous slide. So the steps is, what I did here is I'm combining the step 1 and step 2. Remember what step 1? Step 1 is transforming all the components of the circuit in the S domain, and step 2 is sketching the transform diagram. Okay, so by combining the first and the second step, I have that 3 UT will be returned to be 3 over S. Okay, so you can refer to the transform, you can refer to the table. Yeah, we have learned this in lecture 14 before. Okay, the 2 Henry will now become 2S, yeah, 2S, and in series with a voltage source. Okay, so how we can get this? Okay, so basically this inductor of 2S and this voltage source is a transformation of inductor of 2 Henry. Okay, so to verify this, let's have a look at the transformation for the inductor in previous slide. So I'm going back to the previous slide. Okay, so this is the one. Remember, when we transform the inductor in time domain to a frequency domain, we're going to have the inductor, the impedance of the inductor SL in series with the voltage source of the inductor. Okay, so we're going to have the inductor impedance is SL and the voltage source is Li of 0 negative. So due to that, going back to the problems here, we can have that impedance is 2S while the voltage source is 5 times 2, which is supposed to be 10 volt, yeah, which should be 10 volt. And the resistance, when we transform it, it will remain as it is, so we only have 4 ohm there. Okay, so this is the results of the transform diagram for this circuit. Okay, so hopefully you understand about this. Okay, so remember that step number 3 is to apply the Kirchhoff voltage law in solving for the problem. Remember what is the question here? The question is to find the IT, yeah? Is to find the IT, the current in the circuit. So what we have to do now is to write the equations of Kirchhoff voltage law. We are supposed to get negative 3 over S plus 2S of IS minus Li of 0 negative plus 4 of IS equals to 0. So I've mentioned just now that Li 0 negative is 10. So by then we're going to have IS 4 plus 2S, so 10 plus 3 over S. So you can prove on your own about these equations, yeah? You're going to have IS is 10S plus 3 over S, 2S plus 4. So this is where you need to use the partial fraction. Yeah, so partial fraction for this IS can be written, you can prove on your own that it should be equals to 0.75 over S plus 8.5 over 2S plus 4. Okay, so from this partial fraction equation for the IS, you have to do the inverse of Laplace transform. So when you do the inverse of Laplace transform, you are going to get the IT. Yeah, the IT now becomes 0.75 of UT plus 4.25 exponential of negative 2t of UT. Okay, so you can prove this on your own, yeah, by adopting the things, the method, the techniques that we have learned in lecture 14 previously. Okay, right. So let's have a look at the second example of loop analysis. For these examples, again, we are given two loops here. We're going to have, there is a 3 voltage source, okay, 3 volt. We have a resistor of 1 ohm, resistor of 2 ohm, we have the inductor of L, and we have capacitor of 1 farad. Okay, the question states that find the VT. So what is the VT? VT is the voltage across the capacitor. So find the VT when the switch is connected to A at t equals to 0. So initially the switch is at B when t less than 0. So initially, promptly when t equals to 0 and above, the switch is then connected to point of A. So our assumption in this question is the initial voltage source, V0 negative, is 0. So the initial voltage source here is connected to initial voltage for the capacitor, yeah? Yeah, so V0 negative here is the initial voltage value for the capacitor. So when we transform the circuit into the S domain, we know that when the switch is connected to A, the B will become open circuit. So we can simply ignore the existence of the inductor. So now when t bigger than 0, equals or bigger than 0, the circuit can be then transformed to look like this. The 3 volt will now transform into 3 over S, resistance of 1 ohm and 2 ohms will remain as it is, and the capacitor now will become 1 over S or 1 over SC. Yeah? So 1 over SC, and supposedly there should be a voltage source in series with the capacitor. But since that initial voltage source is 0, so that voltage source can be ignored. So we only have a impedance of the capacitor. So this is what the circuit or the transform diagram should look like. Remember, you are requested to find the VT, which is the voltage across the capacitor. So to find for the VT, first thing first, you need to find the current in the loop. Yeah, find the current in the loop. Okay, so that's why we have this transform circuit. So using the KVL or the Kirchhoff voltage law, we can write the equation to be negative 3 over S plus IS plus 2IS. So this is a voltage drop across 1 ohm resistor, a voltage drop across the 2 ohm resistor, voltage drop across the 1 over S impedance, and equals to 0. So solving for the IS, okay, so you have to use the you have the IS here, which is 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 the current flowing in the circuit. Yeah, we have 3 over 3S plus 1. And from this IS, we can obtain the voltage drop across the capacitor, which is supposed to be 1 over S, impedance of the capacitor, multiplied with the current. Yeah, current of IS. So we have 3 over, when we do the partial fraction, okay, we have to do the partial fraction. We have 3 over S minus 9 over 3S plus 1. So by applying the inverse of Laplace transform, the Vs can be written to be Vt as 3 ut minus 3 exponential negative 1 over 3 t of ut. Okay, so this will be the Vt in time domain, which is obtained from the inverse of Laplace transform from this Vs. Okay, so that's how we solve for the circuit analysis problem using the Kirchhoff voltage law. Yeah. Okay, so the second method is node analysis. So this is where you have or I think you know, yeah, the conditions where you have to use whether node analysis or the loop analysis. Okay, so let's have a look at the steps of using the node analysis. So again, the steps will be similar to the loop analysis. Okay, we have step number 1, which is transforming all the components RLC together with the current source in the S domain. Okay, so this is what we have learned in previous part 1 of the lecture. Yeah, in which if I can recall back, for the resistor is simply the impedance R. For the inductor will be impedance of SL in parallel with the current source. And for the capacitor will be the impedance of 1 over SC in parallel with the current source also. You can refer to the previous slides, yeah, for this case of inductors and capacitors transformation. Okay, number 2 is to sketch, or step 2 is to sketch the transform diagram. Okay, and number 3 is to use the Kirchhoff current law at respective nodes. All right, so let's have a look at the example of node analysis here. Okay, so for node analysis, we are having here problems of 2 capacitors, C1 and C2, 1 farad and 0.5 farad respectively. So we're having V1 as a voltage across the capacitor C1, V2 is the voltage drop across the capacitor C2. There's a resistor of 1 ohm and there's a switch of S. The question is, find the V2T, which is the voltage across the capacitor when the switch S is closed for T bigger than 0. So assumptions made here is the VC1 0 negative is 2 volt and VC2 of 0 negative is 1 volt. Okay, so VC1 0 negative is the initial voltage for C1 capacitor. The VC2 0 negative is the initial voltage value for the C2 capacitor. So which are 2 volt and 1 volt respectively. Okay, so you can refer to the transform diagram for the capacitor. Yeah, so when we substituting uh, uh, the impedance value and the uh, current source value, you are supposed to get 1 over SC, yeah, 1 over SC for the impedance. So C is 1, so that's why we have 1 over S. Whereas for this current source, so it's supposed to be, uh, let's have a look here at the voltage current source. What's the equation for that? Let's have a look for the capacitor. Okay, for the capacitor, it is CV0 negative, yeah? CV0 negative, and the direction of the current source is against the direction of ICS. Yeah, so for this, we are getting, going back to this, we are getting CV0 negative will be C is 1 farad, V0 negative is 2, so that's why we have 2 ampere. The direction is against the direction of this capacitor's current. The same things apply for the capacitor of C2, which is 1 over SC for the impedance value. So 1 over SC, C is 0.5. That's why it is 2 over S. And the current source is CV0 negative. C is 1. Yeah, sorry, C is 1. Sorry, C is 0.5. VC0 negative is 1. That's why we have the current is 0.5 ampere. Okay, so the transform circuit should be looked like this, in which the resistor R will remain as 1 ohm. So this is your transform circuit for this time domain circuit. Yeah. Okay, remember what's the aim? The aim is to find the V to T, the voltage across this capacitor. So now we are going to use the node analysis for this problem. So we're going to have this equation at node A and node B respectively. Okay, so at node A, we're going to have 2 minus V1 over 1 over S minus V1 minus V2 over R equals to 0. Yeah, so this is the Kirchhoff current law at node A, and at node B, the KCL or Kirchhoff current law will be 0.5 minus V2 over 2 over S plus V1 minus V2 over R equals to 0. Okay. So we have two equations here at node A and node B. So we have two equations 1 and 2. So from first equation here, we can write the V2 in terms of V1, which is V1 is 2 plus V2 over S plus 1. You can prove this on your own. And we're going to substitute this V1 in V2 or V2 in V1 terms in S in equation number 2 here. So when we're substituting this equation into here, we are supposed to get the V2 terms, yeah, the V2 terms, which is in S domain. This is readily, we have readily provided to you in partial fraction form, yeah. So you have to work out to get this V2. So you can try this on your own. We're going to have 5 over 3 over S. So 5 over 3S minus 2 over 3S plus 3. So when we do the inverse of Laplace transform, this will become 5 over 3 of ut minus 2 over 3 exponential negative 3t of ut. So this is the v to t in the time domain. Okay, so you can prove this on your own, yeah, to prove the use of Laplace transform in solving the node analysis problem. Okay, so I'm going to stop here. So next, part 3 of this lecture 15, we're going to do a few examples in solving the circuit analysis problem using a Laplace transform. Okay, so see you in part 3 of lecture 15.